Okay, section 3.1, part 2. Welcome to Friday, gentlemen. The homework for tonight over the weekend are these problems here from 3.1. I know it's been a while since you did the first part of the 3.1 homework. You did that Tuesday. That's when it was assigned. The solutions to the 3.1 part 1 homework are posted on Endline under Contents. It's a PDF document, and you can take a look at those. So let's do a little bit more mathematical induction. Let's start with this example, where we want to prove that for all positive integers n, 3 to the 2n minus 1 is a multiple of 8. 3 to the 2n minus 1 is a multiple of 8. And think about what that means. Think about what p of n is and what it means to be a multiple of 8. In other words, what we want to show is that 3 to the 2n minus 1 power, or 3 to the 2n minus 1, I should say, is equal to 8k for some integer k. If we can show that 3 to the 2n minus 1 is equal to 8k for some integer k, then that means that 3 to the 2n minus 1 is a multiple of 8. Okay, so let's follow our pattern of induction. First step is to show that this is true for n equals 1, or in other words, show p of 1. And like we said on Tuesday, this is generally a pretty trivial step. So I'll plug in 1 for n, so this becomes 3 to the 2 times 1 power, or 3 squared minus 1. And that is equal to 9 minus 1, which is equal to 8. And 8 can be written as 8 times 1, where 1 is a positive integer. So therefore, 3 to the 2 power minus 1 is indeed a multiple of 8. Second step, assume p of n and show that p of n plus 1 follows. Okay? So in assuming p of n, what we're assuming that 3 to the 2n minus 1 is indeed 8 times some integer k. What we want to show is t of n plus 1, or in other words, that 3 raised to the 2 times a quantity of n plus 1 minus 1 is equal to 8 times, and let's just say some integer for right now. It's not going to be k, it's not going to be that same integer as above, it'll just be some integer. Okay, so let's start what we assumed, that 3 to the 2n minus 1 is equal to 8k. And let's see if we can get to WTS. So in WTS, I need the power to be 3 to the 2 times a quantity of n plus 1. And if you distribute that 2, it becomes 3 to the 2n plus 2. So here's what I'll do first. Let me add 1 to both sides, and I get 3 to the 2n is equal to 8k plus 1. So to get that power of 3 to be 3 to the 2n plus 2, let's multiply both sides of this equation by 3 squared. Okay, So the left side, by your power rule, is 3, and add those exponents, to the 2n plus 2. Excuse me. And the right side, when you distribute that 3 squared, or 9, you get 72k plus 9. Look at WTS. You want to show that 3 to the 2 times the quantity of n plus 1 minus 1 is equal to 8 times some integer. So let's do this. Subtract 1 from both sides, pull out the factor of 2, and I get 3 raised to the 2 times the quantity of n plus 1 minus 1 is equal to 72k plus 8. And let me do this to the right-hand side. Pull out a factor of 8. And look at the right-hand side. You've got the left-hand side of WTS, 3 raised to the 2 times the quantity of n plus 1 minus 1. And the right side, you've got 8 times this expression, 9k plus 1. We know k is an integer. 9k plus 1 is an integer as well. And the reason why you know that 9k plus 1 is an integer is because since k is an integer, 9k is an integer by closure for multiplication. And since 1 is an integer, 9k plus 1 is an integer by closure for addition. So there you go. There's the proof. Okay, let's try another one here. Look what we're trying to prove. If r is a real number, in between 0 and 1, then r raised to the nth power, where n is a positive integer, will be less than 1. So following induction, show that it's true for p of 1. Or show that it's true for n equals 1. So here we go. Plug in 1 for n, and I get r raised to the first power is less than 1. Do we know that that's true? Well, certainly, because it was part of what you assumed to be true, that r was in between 0 and 1. So again, as usual, p of 1 is trivial. Secondly, assume p of n and show p of n plus 1 follows. Okay, think about what we're going to assume. We're going to assume that if r is indeed in between 0 and 1, then r to the nth power is less than 1. Think about what we want to show, WTS. We want to show that if r is in between 0 and 1, then we want to show that r to the n plus 1 is less than 1. So here we go. Let's start with what we assumed, which is this right here, that r to the nth power is less than 1. Think about where we're trying to get, right here. So the left-hand side of WTS is r to the n plus first power. Look at our current power of r is r to the nth power. So in order to get that to be r to the n plus 1, let's multiply both sides by r. Okay, now let's determine whether the sign flips or if the sign stays the same. Well, r is greater than 0. We know that from the assumption. So r is greater than 0, sign does not flip. This is MPOO, multiplication property of order. Okay, let's just use some algebra here. R to the n times r is r to the n plus 1. On the right, 1 times r is r. Two properties there. One is power rule on the left, and on the right side, that's multiplicative identity. Okay, now look at where we are. I've got r to the n plus 1 is less than r. Now we also have from the assumption that r is less than 1. That was given. So look at those last two inequalities. R to the n plus 1 is less than r, and r is less than 1. Sorry, I think I said that wrong. Look at the last two inequalities. R to the n plus 1 is less than r, and r is less than 1. By the transitive property of order, can't we now say that r to the n plus 1 power is less than 1? That is, as we called it, transitive property of order, or TPOO. That was WTS. That's the end of that proof. I'm going to stop this now, and I'm going to start a different video for the last two exercises because I want to make sure that this can fit on YouTube.